Okay, this is exam 1 for physics 201. First of all, which of these is dimensionally correct? Well, this first one is one of our kinematics equations. So we know it's correct. Let me show you. Meters per second plus meters per second plus meters per second squared times time, which is seconds. That cancels. And so I'm left with meters per second all the way throughout. Here I have kilograms, meters per second squared. That's m times a. Meters per second, that's v. And then 1 over x is 1 over meters. And then I have kilograms, meters per second, that's v, but they're both cubed, because it's v cubed, and then 1 over meters squared. Let's simplify this a little bit. That cancels with 2 of those. And over here, that cancels with that. I'm left with kilogram meters over seconds cubed, kilogram meters over seconds cubed, so that's okay. So far 1 and 2 are dimensionally correct. Kilograms meters per second equals kilograms meters per second squared. That's m and a, 1 over meters. Let's see, these don't look so good. Kilogram meters per second, kilogram over second squared, so that's not dimensionally correct. So B is the right answer. So there's this expression, how many sig figs should the final answer have? Well, if I add these, I keep the lowest number of decimal places. That's going to be 5.0. 5.0 squared is 5.0, 5.0 over 2.54. And when I multiply these two numbers, I keep 2 sig figs, and then I'll be dividing 2 sig figs by 3 sig figs. So I keep the lowest number of sig figs, which is 2. Current standard per kilogram is cylinder in France. What's the new proposed cylinder? Okay, it's not a mass silicone sphere in Australia. That wouldn't be accessible to everyone. It's not the mass required to construct a silicone sphere, 3 centimeters across. I remember in the video, it wasn't the mass, it wasn't the particular sphere that they were constructing. It was in fact the mass of a particular number of silicone atoms. So they're basing the standard for the kilogram based on a particular number of silicone atoms. How many centimeters in a kilometer? Well, 1 kilometer. In 1 kilometer, there are 1,000 meters. And in 1 meter, there are 100 centimeters. So 1,000 times 100 is 100,000. Pencil is about how many meters long? Well, it's about 20 centimeters long. 20 centimeters is equal to 0.2 meters. Actually, a number 2 pencil is 19 centimeters long. Convert 12 meters per second squared to the British system of units. In 1 hour, there are 3,600 seconds. I have to square this whole term. And in 1 mile, I give you the conversion factor there. There are 1,609 meters. Let's see, 12 times 3,600 squared divided by 1,609. Get 97,000. So B. Which of the following weighs about a pound? Well, a kilogram is about 2 pounds. So a half a kilogram is 1 pound. What are the units of this equation? I have meters per second, kilogram, meters, second squared over meters. That's 1 over A. Meter, kilogram, seconds. A is the right answer. You move along this path from point A to point B. What is your displacement? I'm going in this direction. I move 1, 2, 3, 4 units to the left, so it must be -4. Or I could say -1 minus the initial position, which is 3. That's equal to -4. Consider this position versus time graph. Which of the following best represents the velocity versus time? Okay, so I initially have a big positive velocity, and then I have a small positive velocity. All right, because it's positive, that gets rid of this one and this one. Because it starts out with a big positive velocity, it gets rid of this one. So C is the right answer. Your speedometer measures speed, not velocity, because it only measures the magnitude. When throwing a ball straight up, which of the following is true? Well, the velocity goes to 0, but the acceleration is still -10. You drop a rock off a bridge. When the rock is falling 4 meters, you drop a second rock. As they two continue to fall, what happens? Okay, well, they don't stay constant. The velocity of the second rock doesn't increase faster, and the velocity of the first rock doesn't increase faster. In fact, they both increase at the same rate. That is -10 meters per second squared. Now, the rock that you drop first will be going faster, but it will not be increasing at a faster rate. You drop a ball from a certain height. So drop the ball. It initially has 0 velocity, and in the end, it has a velocity that's big and negative. All right, so because it has 0 velocity initially, that gets rid of this one and this one. And because it's velocity at the end is negative and big, that tells us that A is the right answer. So this position versus time graph, what's the sign of the acceleration? Okay, I have a decreasing speed, the slope is getting smaller. I have a negative velocity because that slope is negative, and so that means I must have an acceleration that's opposite the velocity, so I have a positive acceleration of v. All right, consider this position versus time graph. It's an object traveling from y equals 0, and it returns to its original position. So something like this. It goes up, and then it comes back down again. All right. Estimate from the graph the velocity at t equal 1.5 seconds. So I'm just looking for an estimate here. We can actually calculate the velocity very accurately from the function, but I'm just looking for an estimate. So I'm going to sketch in a tangent line there. I'm going to pick a couple points to find the best fit line. Let's pick here. And I'm going to go down to here. You might choose a different line, so you might get a slightly different answer. I'll account for that. And let's see, I have a rise going from about 2 to 8. So I have a rise of approximately 6. And then I have a run going from, what's this, about 1.4 to 2. So I have a run of about 0.6. And actually my rise is negative 6. So for A, my slope, which gives me the velocity, is equal to rise over run. That's negative 6 over 0.6, and that's equal to negative 10 meters per second. Write the function that describes the velocity. Well, my position function is negative 10t squared plus 20t. So my velocity, which is the derivative with respect to time, what was it, negative 10t squared plus 20t, is going to be negative 20t plus 20. And that's equal to my velocity with respect to time. You know what, I can check my my answer for A here if I'm so inclined. At 1.5 seconds, my velocity should be equal to negative 20 times 1.5 plus 20. See, 1.5 times 20, that's negative 30 plus 20. Hey, check that out, negative 10 meters per second. So I was right spot on. All right, that wasn't necessary to answer the problem, but just wanted to check my estimate here. What is the acceleration of the object? Well, A is equal to dv dt, and that's going to be negative 20 meters per second squared. It's just the coefficient of this term. D, how long is the object in motion? Show how you can get this answer. You know, several ways you can do this. The easiest way is just to say, well, it starts here and it ends here, so darn it, it's 2 seconds, all right? So I can just take it from the plot. It shows 2 seconds. There's some other ways to do it. Like the more difficult way is you could say that, well, acceleration is negative 20. V naught is equal to 20 meters per second from that velocity function. And I know that V at the top is equal to 0, and I want to find time at the top. This is sort of the difficult way, but the way we did it in class. And so I can say V equals V naught plus AT. And that's 0 equals 20 minus 20 times T. This is T top. And solve that for T top, and we find that T top is equal to 1 second. So the total time then would be twice that, or 2 seconds. That was D. What is the velocity of the object at t equal 1.1 seconds? All right, well, I already know my velocity function, which I found right here. Negative 20t plus 20. By the way, I just want to show you here that this function is the same as this equation, right? This function is just a rewriting of that equation, right? We just took the derivative to find this function, but so here is my v naught, and negative 20 is my acceleration. So negative 20, I think my time was 1.1 seconds, plus 20, what's that? Yeah, so it's negative 2 meters per second. And that's E. World War II, there were several reported cases of airmen that jumped from flying airplanes. They dropped from 6,000 meters. Then they landed in a snowdrift that allowed their deceleration to be relatively small, and the snow stopped them over a distance of 3 meters. So first, how long did the airmen take to fall to 6,000 meters? Well, first, I got this airman. Oh, he's falling from 6,000 meters. This distance, 6,000. So my y final is equal to negative 6,000. My v naught here is 0, and acceleration is negative 10. So I want to find the time. And then let's go and look at A and B as well. I also want to know what is the velocity at the end. I'll need to know both those values. So I know that v equals v naught plus at. Just write down my equations. We'll sort of assess where we are. Y is equal to v naught t plus 1/2 at squared. All right, so let's see. I don't know t or v. I don't know v. I don't know t. All right, but I know everything in this equation except for t. So I can go ahead and solve this equation for t, which will answer option A, question A. So y is equal to negative 6,000. This term goes away, equals 1/2 of negative 10 times t squared. And let's see, so that's 6,000 over 5. The negatives go away. Square root of that equals t. That's the square root of 1,200, which is equal to 35 meters per second. Or excuse me, not meters per second, that's seconds. These guys fell through the air for 35 seconds. Now, that doesn't seem like very long, but I'm sure when you're falling towards the ground, it seems like forever. All right, so that was part A. And now we can also find part B, and that is what is its velocity. V naught is 0, so I just have negative 10 times 35 seconds. And that's equal to negative 350 meters per second. Awfully darn fast, okay? So the a gun shoots at a bullet goes out about 300 meters per second. Now, in reality, we're not dealing with air resistance here, but they would actually not reach this full speed. They would reach what we call the terminal velocity, which I think is right around 100 meters per second. But we're just going to continue assuming that it's 350 meters per second. Then how long did it take the airman to come to rest when he strikes the snowbank? All right, so now we have a different situation. We have this guy has a V naught equal to negative 350 meters per second. And then he strikes this snowbank and he travels down towards the ground until he comes to rest, and he has a V final down there equal to 0. And I know that this distance, y I'll call it, is equal to 3 meters. And I don't know his acceleration, and I don't know the time. All right, so here we're not worried about the acceleration due to gravity. It's minimal compared to the acceleration due to the snowbank. The snowbank is actually slowing him down. All right, so I think C and D, we want to find both of those things. So we'll treat these in parallel. Let's write down our equations like we did before. Y equals y naught. Or excuse me, I'll just leave off the y naught because it's 0. And then V equals V naught plus AT. Okay, so here I have some unknowns. I don't know T, and I don't know A. I don't know T, and I don't know A. All right, so I don't know either one of those. So I'm going to solve one side. I'm going to solve this side over here for T. I'm going to say T equals V minus V naught over A. V is equal to 0, so that's negative V naught over A. And then I'm going to take this, I'm going to plug it in for T here and here. So I get an expression over here, y equals V naught times negative V naught over A plus 1/2 A negative V naught over A squared. I can simplify this and it becomes fairly simple, negative V naught squared over A plus positive V naught squared over 2A. One of the A's canceled there. Now, I want to find a common denominator, so I'm going to multiply both of these by 2, and I get negative v naught squared over 2a equals y. And I'm looking for a. So I solve this for a. A equals negative v naught squared over 2y. That's negative 350 over 2 times 3. 350 over 6 is 58 meters per second. We'll call it 58 meters per second squared. All right, that's in the positive direction. The velocity is down. He's slowing down, so the acceleration must be opposite the velocity, so it's positive. And now that I know A, I can find T, because I know T is equal to negative V naught. That's negative 350 meters per second over A, which is we just found to be plus 58, and 350, 6 seconds. Oh, let's see. I'm sorry. I made a mistake here, didn't I? So I should have squared this. I thought that time seemed really long. Let's just go back and fix this. I just forgot to square that 350. Hopefully you've already found this. So I have 350 squared over 6. It's 20,000 meters per second squared. All right, much larger acceleration because he's going from a really high speed to a 0. And then let's see if I put that in here. This is still, okay, let me start this over. So T is equal to negative 350 over 20,000. I get 0.018 seconds. Right, that seems more reasonable. Those are our answers. Probably the most difficult problem on the test, kinematics problem. Estimate how many baseballs will fit inside this classroom. I was looking for order, magnitude. I treated the baseballs as cubes as we did in the homework. They're cubes approximately 5 centimeters on square. So the volume, the volume of the baseball is treating it as a cube, length times width times height is 5 centimeters cubed. All right, that's going to be 0.05 meters cubed, and 0.05 cubed is 0.0001. I think it's actually 0.00125, but we'll just go with this. Cubic meters. So that's the volume of a baseball, and then the volume of our room. It's approximately 20 meters long, approximately 10 meters wide, approximately 2 meters tall. So that's 20, 200, that's 400 cubic meters. And then to find the total volume, I just say, the number of balls, I say the volume of the room divided by the volume of the baseball is equal to 400 over 0.001. You get 4 million. 4 times 10 to the 6 baseballs. That's a lot of baseballs. All right. You might have gotten anywhere from 1 million to 10 million, okay, depending upon how you did this. So draw the equations of motion. Let's see, we start with this. V equals dx dt. Dx equals v dt. Integrate both sides. That's x equals vt plus my integration constant. Pardon me, I'm sorry. I was getting ahead of myself. We start with the definition of acceleration. A is equal to dv dt. dv equals a dt. Integral of both sides, integral of dv is v. A is not dependent upon t because it's a constant value, so it's at plus my integration constant. V is equal to at plus v naught. That's my initial condition. And then I say v equals dx dt. Dx equals v t times v. I integrate both sides. I get x then is the integral of v naught plus at. That's what we just found over here, dt. X is equal to then v naught t plus 1/2 at squared plus my initial condition, c, my integration constant. That's my initial position. Looking for those derivations. Let's see, I think this is the last one. Write the functions for velocity and acceleration. I just take the derivative to find the velocity. Is negative 8t plus 3, and acceleration is negative 8. At what time does the object come to rest? All right, that's asking when is v equal to 0, and it's just minus 8t plus 3 equals 0, and I solve that for t, and I find that t is equal to 3/8 seconds. 3/8 seconds. If you want that in decimal form, that's 0.38 seconds. 0.375 or 0.38 seconds. And then c, there's only one time that it comes to rest. At what times is the object y equals 0? So my y function is negative 4t squared plus 3t. So I want to know when does this function equal 0. I can factor out a t. This function equals 0, the position that is equals 0 when any one of these sides equals 0. So it occurs at a time of t equals 0. And it also occurs at a time of solving this for 0, t equal 3/4 of a second. Let me just show you how I got that over here on the side. Negative 4t plus 3 equals 0. Negative 4t equals negative 3. T equals 3/4 second. So that's sort of how I came up with that. All right, so that's c. Those are the two times. All right, so you're throwing it up, and then it's coming back down. It goes up at 0 seconds. It comes down at 3/4 of a second. What is the velocity at t equal 1 second? Let's start it back up here. I have my velocity function, v equal negative 8t plus 3. And then at 1 second, that's negative 8 times 1 plus 3. That's negative 5 meters per second. That's the answer. And then E is draw the velocity versus time graph. Okay, so I know from my velocity function that the initial velocity is 3, and that my slope should be negative. My acceleration is negative. So it's going to look like this. All right, here, this is velocity versus time. The slope equals negative 8. And the initial right here is positive 3. I wasn't looking for those numbers, but just to give you an idea how to draw the graph. And then F, draw the position versus time graph. What initially has a positive velocity. And actually, if you draw this all the way to the end, it's going to look like this. If this is something going up and then coming back down again. So the position versus time graph will look like this. We've seen these graphs. It has a 0 velocity right here. It has a big positive velocity right here and a big negative velocity right here. So that is the position versus time graph. And I believe that's it. There's the multiple choice answers.